In this video, I'm going to talk about some of the more recent research we're doing at Uppsala University. This specific idea is called direct-to data. So first, let's recap what a normal cache hierarchy looks like. So typically, we have a core where the load or store is performed, and we have a TLB where the core can do a lookup to get the physical address, and then the TLB is backed by a second level TLB in case the first level TLB is too small its reach is too small to hold the data set we're interested in. We also have a cache hierarchy, first level cache, second level cache, and the third level cache, which we often call last level cache. If it is the last level cache before we have to go to memory. Also, I'm showing what we normally have in a multi-core system, a network on chip, which connects several cores together to the last level cache. In this example, we're only going to look at a single core. So in this system, there are several possible places where a piece of data could be. It could reside in L1, could reside in L2, could reside in the L3, or it could reside in memory. So when you do a load or a store from the core, the first thing that happens is that we'll do an associative search in the TLB. So that's what this red arrow means, associative search. Out from that associative search comes a physical address that will allow us to make our access to the first level cache. Once more, we will do an associative search here. If this is an 8-way associative cache, we have to look at 8 different address tags to figure out if the data is in the cache, and if so, where it is. If that fails, we need to do what we call a level-by-level search in the cache hierarchy. So we have to go to the next level and do a lookup there by looking at, for example, 8 different address tags. And so on. If we miss there, we go to the next level cache, and so on. And finally, once we figured out that through this serial doing lookup in cache by cache, we figure out it's not in any cache, then we go to memory and we can nail the data. That's all good. So this is what we do in a traditional cache hierarchy. In our scheme, which we sometimes refer to as direct to data, and also sometimes referred to as green cache because it's very power lean, we have some simplifications. First of all, we implement caches without the need to do associative searches in the caches. So that goes away. Since we don't do associative searches in the caches, we can throw away the address tags. That goes away. We also do not need to search the caches level by level by level because we have this property direct to data that will tell us where the data is. So also those searches go away. So this looks pretty nice. So what do we do instead? Well, what we do instead is that in essence we replace the TLB, or we don't completely replace it, but we put it outside of the critical path. So you will not see any picture of a TLB in these designs. And instead we replace it with what we call a location tracker, and that is our single mean of finding the piece of data. So that's the essence of this idea. Still, in our design, there are 4 different places where the cache can reside, and it's still 8-way associative caches here. So in each cache level, there are also 7 other places I'm not showing here where the data may reside. The location tracker, instead of storing a physical address, it stores what we call the location information. So the location information, we encode information about the cache level and the way where each cache line resides. Okay, I'm going to explain a little later exactly how we represent this in the location tracker. We also have a special symbol for memory. So for example, if the data resides in memory, the location information will tell us right away on cycle number 1 that the data we're looking for does not reside in any cache, and we can go directly to the memory. So this, of course, can save lots of latency. If location information says that the data is in L3, we can go directly to L3 and we don't have to search cache by cache like this. So the location information can identify the level as well as the associative way in the cache where the data resides using 5 bits. So it can point to any of the piece of data and we can just go directly and get it. So that's why it's called direct to data, D2D. In essence, the net effect of this compared with a traditional vintage cache is that we can see a shorter latency when we access memory, or cache, and as you will see in a little while, also a much lower power consumption. So here's a quiz. Why is the access time to cache or memory, why is it lower? And here one answer is correct. No, it's not because we don't do a TLB lookup, because we do the location tracker lookup, and this in essence has the same latency as a TLB lookup. So that's not what's going to help us. It's not because it's less associativity, we have the same associativity. It's because we don't need to do the level by level search and can go directly to data. So let's look at how we implement this location tracker. I mean, so far it sounds like a very compelling idea, but we have to have an efficient way of implementing the location tracker, otherwise this will not fly. And so this location tracker has to be able to identify where the memory resides in the cache hierarchy. Here I also added some percentage numbers. So these are from a large set of benchmarks that we've studied. Is the likelihood that a load or a store will hit at a specific level in the cache hierarchy. So 97% of the accesses will hit in L1, 0.5% will hit in L2, 1% in L3, and 1.5% in memory. So if you add up this number, it comes to 100. And as I said before, the location information should be able to directly identify where a piece of data resides. In our research papers, we have proposed what we call the cost-neutral way of implementing the location tracker, or the first-level location tracker, LT1. That means that we try to use exactly the same amount of hardware to implement this whole cache hierarchy as we did in the previous cache hierarchy. So in this example, the location tracker 1 will have the same number of bits, roughly, as the tags we normally use in the first-level cache. So that it's sort of bit neutral. We use the same number of SRAM bits in both designs. In our implementation that we propose, we divide the address space into what we call regions, location tracker regions, and just based on some simple experiments, it looks like a region of 1 kilobyte is about the right size, makes the right trade-off. That means that one of these location tracker regions will track 16 cache lines. So in essence, there will be 16 of these location informations covering all the data that can reside in the region. So this is what it looks like. So inside our location tracker, that sort of looks like a TLB in its implementation. There will be an address tag that identifies the region that's stored at that specific place in the location tracker. And the payload is not the physical address or physical page frame as we used to from the TLB. Instead, it will contain 16 of these location informations, where each one of these information is 5 bits. In order to get this cost-neutral way for this implementation, we just figure out how many of these regions we can put in the location tracker and still not use more bits than we normally use for the address tags in a normal L1 cache. So that comes to 128 location tracker regions. That's what we can have in the location tracker at any given point in time. So the reach of the location tracker is equals to 128 LT regions, or equal to 128 kilobytes. So the reach is still larger than a normal L1 cache, but not as large as an L2 cache, and absolutely not as large as an L3 cache. The location tracker is implemented in a set associative way, so a similar way to how you implement state-of-the-art TLBs. So it's an 8-way set associative cache with 16 sets, so 8 ways, 16 sets. So that's how we come to the 128 regions tracked at the same point in time. And as I said before, we use the same number of bits in the location tracker as we normally use in the L1 tag. So it's a cost-neutral implementation. And it results in a pretty good performance. So the hit ratio in this fairly small location tracker is 99.5%. So much better than the hit rate you normally see in the first level cache. And if you look at how these hits are divided between the different accesses to the different cache levels, what I'm showing here is that out of these 97% of accesses for which the data is indeed in L1, out of those, 99.8% of those accesses we will indeed also hit in the location tracker, in this small location tracker. Out of these accesses that hit in L2, the 0.5%, out of those, 80% of those we will actually hit in location tracker. So even though the reach of this location tracker is not fantastic, it's actually smaller than L2, we have a good coverage here. That may not be so surprising, but what actually did surprise us is that we have very good coverage also for the accesses that are in L3 and also in memory. And the reason for that is that we are exploring spatial locality. So we have, if you miss in the location tracker, we will bring in one of these whole entries here, and that will tell you where not just the cache line you're looking for resides, but also its 15 friends. So these are 15 adjacent cache lines that are also covered by the same region, and that's why we get this fantastic coverage. So it seems to be working fairly well in terms of the statistics. And if you cannot find it in the location tracker, we have a hierarchy, just as you do for TLBs, we have a hierarchy of location trackers. So if you can't find the region you're interested in, then you go to location tracker 2, and there is the same kind of information stored in the same format, so you just read it in. And the access time to location tracker 2 is about the same as the access time to the tags of the second level cache, because here we do cost-neutral implementation, so we have about the same amount of SRAM bits here as the tag bits that we just threw away from the L2 cache, and so on. So we're not really saving any bits here. We're just using the bits that we previously used to build tags instead to implement location trackers in this kind of system. And we do sort of spill fill here. Whenever you replace a region from the location tracker, you put that region in LT2 and so on, and then eventually it will retire to LT3 and eventually we'll just completely throw it away. So that's how we implement the location tracker. And once more, so when you replace an entry from a region that contains a location information that points to, for example, a cache line in L3 at a specific way, so it says it's in L3, it's in way 6. Okay, that's the pointer. So when we replace it, that pointer will still point to the same place in L3 and so on. So when we eventually may need this information again, we can just fill it up and we will be able to find that piece of data. So we've written 2 papers on this, one from December 2013 and one from summer of 2014, where we show that we don't need any tags, we don't need associative searches, we don't need the level-by-level search. We actually can use, this is no longer, doesn't look very much like a cache, it's just ordinary SRAM, there is no address tags, no comparators and so on. So we can have advantage of choosing exactly the most optimal shape of the SRAM. We show that we have low energy, we show that we have short access time if we miss an L1 cache, and we also solve a couple of problems like the aliasing problem. As I said, we threw away the TLB, so we have to make sure we solve the aliasing problem. We did. We present some solutions to how we can tie this to a multi-core solution, tie in coherence and so on. Just to explain how we build the location tracker, I wanted just to refresh your memory of what the VIPT cache looks like. So here we have the normal cache array where we have address tags, we have the data, we have some valid bit and so on. It's an 8-way associative cache. Actually, the number here is wrong. It's not a 16:1 mux, since we have to do 3 plus 3 here, so it's going to be 64:1 mux, because we have to find the word out of the cache line, but we also it's an 8-way set associative cache. So lots of associativity, lots of searching, lots of comparisons, and we also have the TLB here, which in this example is you do a lookup in parallel here, you get the page frame, physical page frame you're interested in out here just on time, so you can do this comparison. So you have physical tags here, you have virtual tags here, and so on. Just wanted to remind you about this picture. What I'm going to do now is to replace the TLB with one of these location trackers. So the first thing that would happen is that we no longer store the physical page frame in the TLB, or rather in the location tracker, and we don't need any of the address tags, and we don't need any of these comparators. So instead, this is what the design looks like. So we have a region the region has an address tag. Associated with the region are 16 location information. I'm only showing 4 here. So you do a lookup, and you can trivially, by looking at the virtual address, figure out exactly which of these 16 location information you're interested in. So you get that one out from the left side, location information from the right side. Then you figure out if, by doing an address comparison between these virtual address tags, if the location information you're looking for is in the left side or right side. And then you choose whichever of those you're interested in. Here I'm only showing the implementation of a 1-level cache. So all we need to store here is location information are 3 bits of information because we have an 8-way set associative cache. So in some sense, what you're going to get out of this mux are those 3 bits that are going to be used to drive this mux here. Mux that's going to correctly choose which of these ways the data is in. So here you see as well that we have thrown away the address tags from this array, and so this is slightly simpler. It's not to scale though. It looks like we cut this size in half. That's not true, because typically the cache line is much larger than the address tag. But we do see substantial saving here, and that is exactly the saving that we have invested in storing as many of these location information blobs as we can in the location tracker. So I hope you can believe that this is sort of a not too much of a revolutionary idea. It's, you know, what we normally implement in a TLB. We just use our bits in a slightly different way. So as I told you here in the previous example, I'm just showing a 1-way cache here. What we really would like to implement is a way that can track the entire cache hierarchy. So you assume now that this is an 8-way cache at each of these levels, so that you will need 3 bits to encode in which way a piece of data resides. Then we need to add 2 bits of information for the level information. So the level information will tell you it's in L1, L2, L3, or L4, where L4 is interpreted as it's in memory. So in essence, what we need to track this cache hierarchy would be 5 bits of information for each location information blob. 16 of those are grouped together, and then we have a single address tag in the location tracker that can identify which region that we store. So what about speeds and feeds here? Is this any better or any worse than existing designs? And this is a picture I took out of one of these papers that we published. So what I'm showing here is the access time to the first level cache. And I'm comparing virtual index physically tagged cache, where we do read out all the address tags in parallel and also read out all the data in parallel, which is a very, from an energy standpoint, very expensive proposition. I compared that with a 2-phase implementation where we read out the address tags first, and only after we've done the comparison with the address tags do we bring out the data. And you can see that design is much slower. It's 45% slower. And what you should compare that with is our optimized implementation of what we call the tagless cache. And here you can see that access time indeed for our cache is about 14% longer, where part of it is from the blue part here is from the location tracker called TLB in the figure. The yellow part here is from just reading out the data. So we sort of do a serial lookup, but we can do it so quickly that our access time is actually fairly low. And then we have some extra overhead that I didn't talk about here, which has something to do with the organization of the cache. So we're almost as fast as the VIPT. That is actually very good news. And this assumes a 32 kilobyte cache, which is the normal size of a first level cache. But if you look at what would happen if you would have made the cache twice as large, you can see that our access time would be about the same, because the data part here in their lookup takes so much more time than in our proposal. And you can also see this as a 16-way cache, associative cache, because you cannot make a VIPT cache unless you increase the associativity, as you may remember. And so the trend here is the larger cache you make, the better is the green cache. And the 2-phase cache, the phased or the serial cache, is steadily worse than what we're doing here. So that was the access time. So we're almost on par for the interesting cache size here. But from an energy standpoint, we're doing much, much better. So we're reducing the energy in more than half with our design compared with the traditional design. And for the details, I have to refer you to the papers to look at exactly why that is. And if you compare the same thing for a 64 kilobyte first level cache, or we would remove almost 70% of all the energy compared with the most common design you will have in caches right now. So it's an interesting proposition. So what kind of energy do you think we are saving in this design compared with a traditional cache implementation? Are we saving dynamic energy? Are we saving static energy? Are we saving both? And just one answer is correct. Will we save dynamic energy? I already told you that from a static energy point of view, we use roughly the same number of SRAM bits as you do in a traditional cache. That means that the static energy will be the same for both designs. But we look up much fewer bits. So after we've done the lookup in the location tracker, after that we don't look at any address tags in any part of the cache hierarchy. So more specifically, we don't look at any address tags in the L1 cache. So that's why we can save so much energy. And actually, I did hide this word here on the slide. It's so to not reveal the answer. It's really dynamic energy. So to summarize this, you can design caches in many different ways. As you've seen in this course, you can do a parallel virtually indexed physically tagged cache, or you could do a serial or a phased virtually indexed physically tagged cache. And in terms of energy, the phased cache is much better because you only bring out the data from the way when you know that that way contains the data, and you only bring out data from one way. Where in the parallel implementation, you do bring out all the data from all the ways in parallel, and data tends to be much wider than the address tag, so that is a big bummer. On the other hand, since you do this lookup in 2 steps, the access time, the clock speed here, so clock speed is lower, which means the access time is longer. Typically, we have to do this in 2 clock cycles, where you can typically do this in 1 clock cycle. So that's a bummer. You can also implement what's called a physically indexed, physically tagged cache, where you first do the lookup in the TLB. After that, you start to do a 2-phase lookup in your cache, and that would be even worse. What we are proposing here is a new way of doing caches, the green cache idea. And the design point that I did talk to you about is the design point discussed in one of these research papers, the micro paper. And what we showed here is they have 53% lower power, and we run at the clock speed, which is minus 14%. Still, it's strictly much better than what you can do in a normal 2-phase cache. So it's a low power approach that's almost as fast. And actually, we do make it strong case you can actually implement, we think you can implement our kind of cache as fast as the parallel cache, but we haven't physically done that implementation. So for now, you have to just we have to stay with what we can prove, which is a slowdown of 14%. If you're interested, here are the 2 papers that I talked about, and these links should take you directly to those papers. If you access these papers from the university, I think you'll have free access to these papers. Otherwise, these are research papers that's been published, and they are copyrighted, so you may have to look for these papers in the university publishing system called DIVA if you do this from home, but from the university you should have access to these papers. And the take-home message here is there is a saving. More than half the energy of the dynamic energy is saved, and the other paper makes the case that you can make accesses to the L2 cache about 40% faster, because you don't have to do the serial lookup level by level, and can get there in a single hop. So that's why we call it direct to data. When I talk about cache coherence and multi-threading, I will continue this discussion a little bit and tell you how we expanded this idea into the multi-core world.